For P, I've perspicaciously produced a profoundly pithy poem. Some science is good, some science is bad, some science is salty, just a tad. A scientist worth his salt will usually ask, where's the p-value? P-values can be considered the salt of statistics, always served up reverently. A study with a significant result will report p-values less than 0.05. A good study will report p-values less than 0.01. A study with p-values less than 0.001 might be hiding fraud. Teachers drone to sleepy classes, about p-values of 0.05, you see. The null hypothesis, 2 tails, never 3. T-tests, the F-test significance, Z. And some sweet lady with a bunch of tea. The 4 things I drone on about are the mean, the standard deviation, the confidence interval, and the correlation coefficient. I have called them the average, average error, improved error, and comparator, and sometimes called them the mean, the RMS error, error with sample size, and comparator. I would like even more descriptive simple names, but this is the best I've come up with. Statistics courses often use lots of different names too, but mostly to confuse the issue, like calling the standard deviation sigma. It seems the droning never stops about sigma, x bar, x hat, t, chi-squared, various types of r, and the ever-popular p-value. I won't drone on about p-values even here because confidence intervals are more my mantra, usually a 95% or 99% confidence interval, often shortened to a fractional form of 0.95 CI or 0.99 CI, or even quicker, 95 CI or 99 CI. Adding and subtracting the CI from the average gives a range of numbers. Here is a way of interpreting the ranges. With 95 CI, the odds are 95 out of 100 any new measurement will be in the 95 CI range. With 99 CI, the odds are 99 out of 100 that any new measurement will be in the 99 CI range. Relating confidence interval to p-value is simple. If we subtract the fractional CI value from 1, the result is the p-value. 0.95 CI corresponds to 0.05 p. 0.99 CI corresponds to 0.01 p. And 0.999 CI corresponds to 0.001 pi. The CI talks about what is. The p-value talks about what isn't. Here are the spreadsheet functions for the mean, standard deviation, and confidence interval. The mean, or average, is gotten with the average function. The standard deviation is gotten with the STDEV function. The confidence function calculates the confidence interval for a given p-value, standard deviation, and sample size. For less than 30 samples, the confidence.t t function is often the recommended choice. The confidence interval is easier to understand and use than the p-value. The confidence interval and the standard deviation both work the same way, by adding and subtracting from the average to give a range of values. If you understand how to use the standard deviation, no new concepts are needed to use the confidence interval. With p-values, on the other hand, there are several new points of confusion available. Understanding the p-value formulas and concepts requires work and extra knowledge. Since trust in statistics requires understanding at least some of it, the more you have to learn, the less you trust. Even conspiracy theorists and journalists might learn 4 or 5 simple formulas. So I want to keep the whole statistics course to 4 or 5 simple formulas. I suspect many professionals learn statistics by rote, plugging data into an expensive statistics program without thought. Someone who understands what's going on can make rough calculations to see if the program is on the right track, or even do without the pricey program. Here are 2 rough calculations for confidence interval, or CI. 2 times standard deviation divided by the square root of the sample size is a rough calculation of the 95 CI. 3 times standard deviation divided by the square root of the sample size is a rough calculation for the 99 CI. Dividing by the square root is a conservative way to add sample size to error calculations, since 10 times more measurements improves the error estimate by only 3 times. This is why polls and surveys often stop at around 1,000 samples. To narrow the error range by only 3 times more would require 9,000 more samples. Here is a discussion of sample sizes. Obviously, the more samples, the better. In a professional situation, however, collecting samples costs money, so the fewer samples, the cheaper. This leads to the perennial first question: what is the sample size in this study, Mr. Professional? Journalists almost never ask. Conspiracy theorists never want to know. Journalists construct their stories from a sample of 1. Conspiracy theorists construct their stories with no data at all. Here is some common sense about sample size for those of us not sensationalist news hounds or conspiracy nut jobs. 0.05 is 1 out of 20. 0.01 is 1 out of 100. It makes sense to me, therefore, that any estimation of 0.05p or 95 CI would require at least 20 samples, and any estimation of 0.01p or 99 CI would require at least 100 samples. In a spreadsheet or statistics program, it's easy to plug 0.01p in and get an impressive 99 CI confidence interval with only 2 samples. It's harder to argue that it means anything. Here are 3 experiments, with fake data, of course, in the best tradition of statistics texts. In each experiment, we set up 2 groups of subjects, a control group and a test group. Measurements are taken before and after the experiment for each subject, and the values are subtracted to see the possible change. The 95 CI and 99 CI ranges are calculated for these control and test groups. The first experiment. Here are the 95 CI ranges. Here are the 99 CI ranges. The 95 CI ranges and the 99 CI ranges of the two groups are both widely separated. In a journal paper where p-values reign supreme, it would be possible to state the result as significant when p equals 0.01. The second experiment. The 95 CI range is separated. The 99 CI range overlaps. With overlap at 99 CI and separation at 95 CI, this would be reported as a significant effect when p equals 0.05. The third experiment. Here is overlap at 95 CI, and here is overlap at 99 CI. If there's overlap at both, we don't write the paper unless to debunk some already published crap. We did the experiment and found no significant effect. From this, we can conclude that Weissenstein has the scientific acumen of a toothless butterfly. It is our studied opinion that his craven union of discalced Fisherites be disbanded and their grant money be dispersed to us. Disbanded and dispersed is our gentle suggestion. Disbanded and dispersed, especially dispersed. Here is a simple summary. The average or mean is a simple concept. Add up and divide. The standard deviation, RMS, or root of the mean of the squares, is a little harder, but still manageable. Subtract each value from the mean, square to get all positive values, average the squares, and square root the average. Dividing the standard deviation by the square root of the sample size sensibly incorporates the number of samples in the error estimation. Increase samples by 10, improve confidence by 3. Multiplying by 2 or 3 to get the rough 95 CI or 99 CI is also easy. The average plus and minus a CI gives a range. If all the test and control ranges overlap, the experiment is a failure. If the 95 CI ranges are separate, report the result as significant at 0.05 p. If the 99 CI ranges are also separate, report the result as significant at 0.01 p. Simple. For those wanting the actual numbers instead of 1, 2, and 3, here is a short table. This table can be generated in a spreadsheet by using the function equals confidence, paren, p-value, 1, 1, close paren. The standard tests yielding p-values are good for professionals. The good old confidence interval makes more sense for the rest of us. Thank you.